Hello, welcome back. For this video, we will be looking at the second part of the qualifying stage of the 28th Philippine Mathematical Olympiad. So this one is the second part, which is a bit harder than the first part. And if you haven't watched the video on my solutions on that one yet, I suggest that you watch that first before this one. Okay, let's start with the first problem. We are given f as a function in the real domain, such that f of 2025 minus x equals negative 2 times f of x plus x cubed for all real numbers x. The question is, what are the last two digits of f of 2025? When given with functional equations like this and you are asked for specific values, the good first step is to look at what if x is equal to what you are looking for. I mean, what the input value is being asked for. In this case, we're looking for f of 2025. So perhaps it's a good idea to look at the values of x where you'll get 2025. Know that if you do 2025 as a value of x in the equation, you'll get f of 2025 minus 2025 here, which is f of 0, and then 2025 here. So perhaps the values that we should be looking at are at x equals 0 and at x equals 2025. You feel me? Okay. So let's try x equals 0. If that's the case, then we get f of 2025 minus 0. So that's f of 2025 equals negative 2f of 0 plus 0 cubed. And then let's look at x equals 2025. We'll get that the left side is f of 0, and then the right side is negative 2f of 0 plus 2025. No, sorry, negative 2f of 2025 plus 2025 cubed. Now note that if you let f of 2025 and f of 0 as two variables, then we basically have just a system of equations, linear equations in two variables, which we could easily solve perhaps using elementary methods, one of which is a substitution method. Since we're given here f of 0 in terms of f of 2025, we can just plug that value into the first one. And that's exactly what we'll do here. Substitute f of 0 equals negative 2f of 2025 plus 2025 cubed into the first one, and you'll get this. Now simplify by distributing the negative 2 on the last term to get f of 2025 times 4 minus 2 times 2025 cubed. And then solve for f of 2025. Again, f of 2025 here is our variable. So we'll get this as 4 minus 1 times f of 2025 is equal to 2 times 2025 cubed. Okay, I hope you can follow and fill this part. Then you simplify this and solve for f of 2025 by dividing both sides by 3. So the actual value of f of 2025 is 2 times 2025 cubed all over 3. So what's left is evaluating this expression right here. Since we're not actually interested with the exact value and just the last two digits, we can do some tricks in evaluating this. So we know that 2025 is divisible by 3. So we can factor out 3 out of one of the 2025 here. So we'll get 2 times 2025 squared times 3 times 675. So we can cancel out the 3 here. If we do that, we get this expression. And since we're only looking at the last two digits, we can actually work in modulo 10, in modulo 100, which means that we're just looking at the last two digits for each factor right here. If we do that, the first one is 2. The second one is 2025 squared, which is 25 squared, which ends in 25. And the last term is 75. Multiply everything and then just look at the last two digits to get that the last two digits are 50. Okay, so the last two digits is 50, and the answer is letter C. Of course, if you're not comfortable with using modulo 100, you can skip this part and just evaluate this product right here. If you do that and then look at just the last two digits, you'll still get the last two digits as 50. Okay? Okay, okay. Next, question number 2. Dan is playing a carnival game where he has to shoot down in sequence 8 circular targets, which are arranged in 3 columns as shown below. Each time, however, he can only shoot the lowest remaining circle of a column, and then this target is removed. There is a special prize if Dan shoots the middle circle of the second column, marked in the figure as the shaded black or shaded blue one, as either his fourth or fifth target. Assuming Dan is a sharpshooter who can hit any target he chooses, in how many ways can Dan shoot the 8 targets so he gets the special prize? I hope you understood the problem. So basically, we're looking to get this this shaded part as the fourth or fifth target out of these 8 circles. The restriction, however, is that for each column, you can only shoot the lowest part. Okay, so let's try to hide this question first because it's a bit long. So if we put this here and then remember that the goal is to hit the marked circle as a fourth or fifth target. Now remember that if we are trying to hit the X target, let's say fourth, fifth, or whatever, the number of ways to get that is or can be expressed as the number of ways we can hit the targets before and after that. Okay? So that will be the flow of our solution. Now to make the discussion easier, let's try to label these circles as per column. Let's call the first one as column A with the dots as the circles as A1, A2, and A3. And then the second one as column B, B1, B2, and B3. And then the last one as C1s and C2. Okay, and then as I've mentioned earlier, the number of ways to hit the marked circle as X target is equal to the number of ways to hit the circles before the target multiplied by the number of ways to hit the circles after the target. You get it? This is a consequence of or following the fundamental counting principle. So for example, if we're trying to hit this B2 as a fourth target, we basically want to find the number of ways to hit the first 3 targets before that and then the 4 targets after that, right? I hope that's clear. If that's clear, then let's look at the two possible cases. Case one is that we're trying to hit the circle, the marked circle, as a fourth target. If that's the case, as I've mentioned, we have to hit three circles first before B2, right? And it's important to note that since we have to hit B3 first before we can hit B2, it must always be that this red part here or red group here must contain B3. We must hit B3 first before we can hit B2, right? And then the green one, the number of ways to hit the circles after the target, we need to hit 4. 4 circles after B2. And then of course, since we only hit up to B2 as a fourth target, then after that we must hit B1. Okay, so this part actually here must always have B1. So let's look at the possible configurations of having 3 circles before B2. One possible way is that you get 2 circles from the first column and then one B3. So we can have A3, A2, and B3. So we put that in notation here as 2A and 1B, meaning two circles in column A and then one circle in column B, right? And then after hitting the B2, what's left with us is this A1, B1, C1, and C2. So in notation, we put that as 1A, 1B, and 2C, right? I hope that's clear. So this is one configuration of hitting the shaded circle as a fourth target. Of course, there are other ways. Another way is that you hit A3 and then B3 and then C2. So that's also one configuration. And then after that, of course, you'll have two A's and then one B and then one C, right? In each case, note that the sum of the numbers here should always be 3. In the red part should be 3, and in the right part should be always 4. Okay? Are there any other possible configurations for this one? We have one more, which is when we hit. Oops, I think I made a typographical error here. This would be 0, 0A, 1B, and 2C. 0A, 1B, and 2C. So if we do that, we're basically picking both of this and then just this B3. And then the right side should be 3A. 3A and then 1B and then no C. 3A, 1B, and 0Z. Again, they should be 0. The A here should be 0A. Okay. Is that clear? I hope that's clear. Now, for each configuration, we count the number of ways to arrange them. For the first part, we are technically arranging them, three of them. So the overall or the total here should be 3 factorial. Except that we are constrained that the A3 and A2 must always follow in one order. That is, the A3 must always be hit before the A2. So we have to divide this by 2 factorial. The 2 factorial factor here restricts the number of arrangements for column A. You get it? And then the 1 factorial here restricts the number of ways for column B and then the 0 for column C. Of course, 1 factorial and 0 factorial are just both 1. So technically, we're just being constrained by this 2 factorial here. And if you evaluate that, we have 3. So there are 3 ways to pick here, right? I hope that's clear. If you want to list all of that, that's fine. So you can do A3, A2, B3, or A3, B3, A2, or B3, A3, A2. So those are the 3 ways to arrange the 3 of them. Okay? Now this one follows the same procedure. You have here 4 factorial divided by 1 factorial, 1 factorial, 2 factorial, which is 12 ways. Okay, I hope that's clear. Now do the same for the rest. There's 3 factorial over 1 factorial, 1 factorial, 1 factorial. Then the right side is divided by 2 factorial. And then here should be 0 factorial, 1 factorial, 2 factorial. And then here should be 4. 4 factorial over 3 factorial. Right? So as I've mentioned, to get the number of ways for each case, you multiply this red by the blue, by the green. So the total number of ways to hit the marked target as the fourth target is 3 times 12 plus 6 times 12 plus 3 times 4 for a total of 120 cases. Okay. I hope we're making sense here. I hope it's clear. I hope you have followed so far. So that's the first case. The case that the target is hit as the fourth target. And we have said that there are 120 ways to do that. Next, we look at what if it's the fifth target. If it's a fifth target, the procedure is just the same. But this time, we must hit 4 circles before B2 and then 3 circles after B2. And then just we list possible, all the possible configurations here. One possible way is that we have 3 from column A, 1 from column B. So after that should be 0A, 1B, 2C. Another case is 2A, 1B, 1C. And then the green part of that will be 1A, 1B, 1C. Lastly, we'll get 1A, 1B, 2C, and 2A, 1B, 0C. Again, in each case, for the left side, the total must be 4, and then the right side must always total 3. So 1 plus 1 plus 1, 2 plus 1 plus 0, all of them should be 3 here. I hope that's clear. Then to count the number of ways, you use the same method as earlier, 4 factorial divided by this one being constrained, this 3 factorial. Then the right side will be 3 factorial over 0 factorial, 1 factorial, 2 factorial, and so on. Do the same for all. The numbers are not that big, so it should be easy to calculate. And then ultimately, again, we multiply the red with the green and then add them up. So the total for the fifth target is 4 times 3, 12 times 6, 12 times 3, for a total of 120 as well. Okay, I hope it's clear here. So again, for the fifth case, we have 120 ways. To get the total, you just add up the two cases. So the total is 120 plus 120, which should equal 240. And that's our final answer. So the final answer here is letter B, 240. Okay, I hope that's clear. So the important thing here is to note that the number of ways to hit the mark as the X target is the green one times the red one, and that you have two cases here. The case that it's the fourth, and then the case that it's the fifth. There are other ways to solve this one. Some people shared solutions for this one, which I saw. They use complementary counting, and that's fine as well. That method is just basically practically the same as this one. And I don't think it's any easier than this one, so up to you to choose which method you prefer. Okay, so that's it for number 2. We'll look at number 3. Number 3 is a geometry problem. We are given a regular heptagon ABCDEFG, where point X lies on segment BF such that Fx plus Fg is equal to DG. The measure of angle XVF is X degrees. We are asked to find the integer closest to X. So as with any geometry problem, I think the good first step here is to illustrate, make a diagram of what the given problem looks like. So when you're given with, or the problem involves regular polygons, I suggest that when you draw, you always consider a unit circle or a circle that circumscribes the given heptagon or the given polygon. So in this case, we have this black circle. Draw 7 points here for the heptagon, then the segments. And then we're given point X lying on BF. So we draw segment BF here, and then X somewhere in that line. Now, to be honest, when I saw first of this problem, I was a bit baffled. Because we're given that Fx plus Fg equals Dg, and Fx, Fg, and Dg are not even part of the same line. I mean, they are scattered all around. We have here Fg here, Fx here, and then Dg here. Dg is here. It's quite baffling, and it took me a while before I was able to answer this problem myself. And then to proceed with this problem, The next logical first step, the next logical step here is to consider what's known to you or known to us. In this case, we have x positioned here, and we should know that by or segment addition, we have fx plus bx being equal to the total line fb. So again, that's fx plus bx is equal to fb. Still, that alone does not help us solve the problem until we realize that fb and dg must be congruent. Because this is a regular heptagon, the segments connecting any two of them separated by the same number of vertices should always be congruent. For example, this consecutive segments here should always be congruent because it's a regular heptagon. Meanwhile, BG should be congruent to GE because they're separated both by just one vertex. In this case, BF and DG are both separated by two other vertices. So they must be congruent. I leave it up to you to prove that on your own. I think that should be a good exercise as well. But for this one, let's just say or make use of the fact that they should be congruent. So FB must be equal to DG. And if you look at this, the first one, fx plus fg equals dg, and the second one, fx plus bx equals dg, we should be able to conclude that fg must be equal to bx, right? So bx here should be equal to fg. Since fg is one side of of this regular heptagon, it just means that bx should be also equal to the rest of the sides. So bx length should be equal to the polygon's side length. Okay? Okay. So with that, we're still a bit far from where we want to be because we're looking for the angle. We just we're just able to play with the side lengths. To be able uh, to get this xgf here, we should draw a line connecting g and x. And I have this hypothesis here that if you draw a line from g to x, that should also pass through c. Based on this diagram, it's quite clear that that line should pass through C as well. So let's make a claim that if x is a point here on this line, such that bx is equal to the side length of the heptagon, it must be true that x is also a point on this diagonal CG right here, or this side CG. Okay, so in this diagram, I draw a line CG which passes through x. Okay. So, but for now, let's assume that we don't know this point to be x. Let's just call this for now a point, let's say y. So our goal is to prove that y is actually x. That the point that we're talking about here, this intersection point here, should be the point x, which is, or whose distance from point B should be the same as the side length of the heptagon. Okay? So let's just draw two lines here, BG and CF. These lines could be helpful somewhere down the line, so might as well draw them now. Let's also make use of the fact or the theorems involving angles. One of that I think I've mentioned as well in the part one of the solution for the qualifying stage is that the intercepted arc whose two endpoints are consecutive vertices of a regular heptagon should measure 360 degrees over 7. So this GF right here should be 360 degrees over 7. AG should be 660 degrees over 7. And then the corresponding inscribed angle should measure 180 degrees over 7, half of that. So for example, if GF is 360 degrees over 7, then GCF should be 180 degrees over 7, right? Okay, so let's use that fact to say let's find the measure of this one. GBF, its measure should be 180 degrees over 7, and then BFC should also be 180 degrees over 7, right? So that's just two examples for this one. I hope that's clear. Please take note of this because we will be using this theorems later in the solution. While we're here, since we're able to show that both of them are or measure 180 degrees over 7, we can conclude that CF is parallel to BG by the converse of the alternate interior angles theorem, right? Right? I hope you get it. This is not important actually. This parallel lines being parallel lines is not important to the solution, but I just figured it's worth mentioning here. Okay. Now let's look at our main goal. Again, our goal here is to show that point Y is point X. Note that this angle here, CYB or BCY, shown in green, is equal to 1/2 of the sum of these two angles here, of these two arcs here, GF and BC. This is one of the known theorems in intersecting chords, is that the angle, the angle measure of this one should be half of the sum of the two intersected arcs. So it's 360 degrees, 360 degrees over 7. Half of that sum should be equal to 300 degrees over 360 degrees over 7. Right? Now note that this angle here, this angle, green angle, BCG, should measure 2 times 180 degrees over 7 because this angle here has two intercepted arcs, right? So if you draw a line here, a segment here, you'll get two 100 degrees, 180 degrees over 7. So its total measure should be 2 times 180 degrees over 7, which is equal to 360 degrees over 7. Now, the important thing here is that we have shown that CYB and BCY both measures 360 degrees over 7. So they must be congruent. And if they are congruent by the isosceles triangle theorem or the base angle theorem, then the triangle BCY must be an isosceles triangle, right? The base angles are congruent, so this must be an isosceles triangle. Moreover, we can say that BC must congruent to BY. And since BC is a side length, then we can say that BY is equal to actually FG as well. So we have concluded here that Y is a point on line BF that is FG distance or FG far from point B. And it also lies on the segment CG. Therefore, we conclude that point Y is actually point X. And we have proven our claim. Get it? I have to get it. We have proven here that X is on the segment CG, right? I hope that's clear. And now once we know that, we can remove that explanation there and then proceed on finding the value of XGF. This is XGF. So I forgot to change this one. Again, this Y point Y is this point X. So we're looking for XGF. So now, to do that, we note that BGY has a measure of 180 degrees over 7 because it's the inscribed angle of this intercepted arc. And then BGF, this one here, BGF, this is an inscribed angle for intercepted arcs BC, CD, DE, and FE. So there are 4 of them. So the measure of BGF should be 4 times 180 degrees over 7, which is 720 degrees over 7. So its measure must be 720 degrees over 7. Meanwhile, oops, sorry. I think I made a wrong label here. No, 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 never mind. It's a right label. So next, we're looking for this angle, this yellow golden angle here. We call this XDF, and its measure must be equal to the difference of BGF and BGC, right? So it's 720 degrees over 7 minus 180 degrees over 7, which is equal to 540 over 7, right? This is the angle addition postulate. BGC plus XGF must be equal to BCF, or BGF, right? All right, all right. So the answer we're looking for here is that the closest to this angle, which is 77. Okay? The answer is 77. And that's our final answer. This is a very good problem, in my opinion. So I hope you understood my explanation. If you're still confused, just let me know in the comments. Okay? That's it for this item. Let's look at the next one. Let's look at number 4. Number 4 is a bit of a number theory problem. Let A, B, and C be positive integers such that 3ABC plus 2AB plus A is equal to 343. We're looking for the value of A plus B plus C if none of A, B, or C is a square. Okay. Let's look at the given equation. We're given with just one equation with 3 unknowns, so definitely we will not be able to find complete answers from this using that equation as well. So let's examine that anyhow. Note that we can factor out the A. So we get that A times the quantity 3BC plus 2B plus C being equal to 343, which is equal to 7 cubed. And we're given that A, B, and C are integers, so it must follow that A and this quantity here should be both factors of 7 cubed, right? I hope that's clear. Now, since A, B, and C cannot be perfect squares, and they are factors of 7 cubed, A is a factor of 7 cubed, then the only possible values of A are 7 and 7 cubed. The other choices are 1 and 7 squared, both of which are perfect squares. So the only possible value here is 7 or 7 cubed. So we will examine two cases here, A equals 7 and A equals 7 cubed. If A equals 7, we substitute that to the factored form we got earlier. We have here 7 times the quantity 3BC plus 2B plus 1 equals 7 cubed. Divide both sides by 7. We get the right side to be 7 squared. And then put the constant on the right side, simplify. So that's 7 squared minus 1. That's 48. So we get 3BC plus 2B equals 48, which we can factor out the common factor, which is B. So we get B times 3C plus 2 equals 48. Again, we can conclude the same, or we can use the same reasoning as the one we used earlier. Since B and C are integers, then we conclude that B must be a factor of 48 as well as 3C plus 2. Okay? Moreover, note that 3C plus 2 is never divisible by 3. Because 3C is divisible by 3, if you add 2 to that, it will never be divisible by 3 when we're talking about integer values of C. Therefore, we can conclude here that B must be a multiple of 3. Okay? So we conclude that B must be a factor of 48 and a multiple of 3. So the only possible values of B here are 3, 6, 12, 24, and 48. Again, you don't have to make a reasoning like I did for the multiple to make D a multiple of 3, but it's a good step to reduce the number of values to check. Because if you don't do that, you will be looking at all factors of 48, which includes 1, 2, 3, 4, 6, 8, and so on. But with this one, we have only 5 possible values of B to check. Okay? And for each value of B, we solve for the corresponding value of C. If B equals 3, we can solve for C. So 48 divided by 3, that's 16. 16 minus 2 is 14. So C is 14 over 3. And 14 over 3 is not an integer. So this is not a possible solution. Next, what if B equals 6? We get the value of C equal to 2. So we have the ordered pair 6, 2. B equals 6, C equals 2. Both of them are integers, so this is good. What if C equals 12? The value of C is 2/3. Again, no. Do the same for 24. You get 0. That's not a positive integer. So that's no as well. 48, we get negative 1/3. No as well. So the only solution here is 6, 2. So again, A here is 7. So the value of A plus B plus C is 7 plus 6 plus 2, which is 15. So the answer here is 15. So are we done? 15 is in the choices, so maybe we're done. But for the purposes of being thorough, we still have to check the other case. The case where A equals 7 cubed. If A equals 7 cubed, again, we substitute that to the factored form we got earlier. Divide both sides by 7 cubed. We get 3bc plus 2b plus 1 equals 1. Simplify and factor, we get b times 3c plus 2 is equal to 0. Now, by the zero property of equality, one or both of b and 3c plus 2 must be 0. We want them to be both positive integers, so b cannot be 0. And c cannot, and this 3c plus 2 cannot be 0 as well, because we'll get negative 2/3. In other words, there are no solutions for this case. Okay? I hope you got my reasoning here. B cannot be 0. 3c plus 2 cannot be 0 as well. So we conclude that the only solution for this problem is 762, and that the required sum is A plus B plus C is equal to 15. And that's our final answer. Okay, the final answer here is 15. I hope that's clear. If that's clear, we'll look at the last problem for this video, because it's taken a bit of time already. So let's look at number 5. We're given a rectangle ABCD such that AB equals 6 and BC equals 8. Let X and Y be points on segments BC and CD respectively, and let Z be the midpoint of segment BA. If M is the minimum value of AX plus XY plus YZ, then M squared is what value? Okay, so if I'm to guess, just to guess here, just giving you an idea of how to eliminate the choices. We're looking for the possible value of M squared here. So probably the value of M is not an integer. It's very likely, unless the examiners are testing us. So if you really don't know how to solve the problem, you can use that sort of elimination and conclude that 289 and 256 are likely not the answers, because both of them are perfect squares. So the only choices here are 255 and 288. So if you will have to make an educated guess, not educated, but maybe a strategic guess, maybe it's either A or C. Of course, the examiners can always play with you. So maybe that's not the best solution. And that's why I'm here. I'm trying to explain you the best way to answer this problem. Okay, so let's look at the best solution for this problem, quote unquote best, because that's what I think is the best solution for this problem. Okay, so let's draw the rectangle ABCD. We're given that AB equals CD equals 6 because it's a rectangle. And then BC is equal to DA is equal to 8. And then we're given points X on BC, Y on CB, and Z as a midpoint of DA. Since it's a midpoint, then AD must be congruent to ZD, and the distances must be AZ equals ZD equals 8 over 2, which is 4. Okay, so that's what we know so far. We're looking for AX plus XY plus YZ. This one is AX, this one is XY, and this one is YZ. We're looking for the sum of their lengths. Now, most of you probably, I think that's including me in the past, you might want to set up equations right here. Like maybe you set up this value as m, and this one as 8 minus m, or this one as n. This is 6 minus n, something like that, and then use distance formulas to get these distances. And that is fine, but that's quite difficult, to be honest. You'll have a hard time finding the minimum value of that because you'll have 3 square roots there. Square root of this one, square root of this one, square root of this one. You get what I'm saying? You'll get very big, very messy algebraic expression right here. So for this one, the best solution is to make use of symmetry. Symmetry and reflections. So I'm not sure if you're familiar with that yet. So please pay attention to the next points that I will try to make. So the next step here is to reflect this rectangle about the side BC. So if you do that, you have reflected this side to that one. So you have A going to another point. Let's call that A1. And then D goes to D1. Yes? Now this point Y should also be reflected about point C. You reflect that here. And then your Z should be still here in the midpoint of DA. So we do that reflection. So it's here. Again, this point Y here should be in the same position as where it was when it was here in the segment CD. Okay, we're not done yet. We'll do another reflection. Reflect this rectangle A1, B1, CB about this side here, about this side CB1. If you do that, you'll get this rectangle here. You have A2 and B2, and this time we can reflect Z. Again, Z must be the midpoint of this segment. So ZD1 should be 4 again, 4 units, like this original given. Okay, I hope that's clear. Now I hope you can see where this solution is going. If you can't see it yet, that's okay. So let's say the sum of their distances is S. So S is AX plus XY plus YZ. Let's call that X. And because I did this through a program, then I can easily find the length of this AX at any time. So in this configuration that I'm showing right now, the length of S, the total length is S equals 17.56. We can try moving X and Y somewhere here. Look at the values. It's reducing. At some point, it decreased to below 17, but suddenly it went up above 17 again. I hope you saw that. It's from 17.5 to down to 17. and then again up, higher than, excuse me, higher than 17 again. Of course, you will not be able to see that kind of simulation on your paper, on your when you do it manually. But I'm just trying to give you like some sort of motivation where this solution is heading into. So if we trace back our animation earlier, note that this is the smallest value of S that we have gotten, 16.97, which we see happens when this is a straight line. Ax, xy, and yz are part of the same line, which makes sense because the shortest distance from A to Z should always be the line through the line connecting A and Z. The other configurations just makes the length longer because it's like you making a detour, right? I hope that's clear. So the shortest distance is this segment, gold segment here, A to Z, right? Right. So what's left is to find the length of AD. Now to find that, we can draw a right triangle here, this gold right triangle here, and the sides of this one is known or can be known. For the bottom leg, we know that to be this side here, which is 8, BC is 8, and then D1Z is equal to 4. So this total length here is 12. 8 plus 4 is 12. And then the vertical one, these are just two CDs. CD, CD, so that's 6 times 2. So that's 12 as well. So by the Pythagorean theorem, the minimum value of S should be the square root of 12 squared plus 12 squared, which is 144 plus 144, which is 288. So the value of S squared, the minimum value is 288. Actually, the right variable here should be M. The value of M squared should be 288. And that's our final answer. 288 is our final answer. If you approximate, if you approximate the S here, this should be S. S is approximately 16.97, or M is approximately 16.97, which is what we got using our simulation earlier. Okay? So again, just to recap this one, what we did here is to make use of reflections, symmetry and reflections. Whenever you're looking for, you're solving problems like this one, I suggest that you try to explore reflections and symmetry because that will likely simplify the solution. And usually the ending of that method is you finding the shortest distance between 2 points. Normally that's the ending. Okay? I hope you understand that. Anyway, that's the first 5 problems for the second part of the qualifying stage. It took me a while because the problems are quite harder, much harder than the part one, definitely. So the questions 6 to 10, I will record that and upload maybe sometime next week or next week. So stay tuned for more videos. If you have any comments, suggestions, violent reactions, just let me know in the comments. Okay? Thank you for watching and see you on the next one. Bye.